Hello everyone, sorry for the technical break. Thank you for having me, first of all. And I'm going to talk today about my and my team's experience with running AsyncIO in production. So as you can probably hear, my voice is not fully functioning. So apparently, if you live in Krakow and you travel to a city that's not as toxic as Krakow is, you lose your voice. But hopefully it'll last me till the end of the presentation. Okay, so I live in Krakow and I work at Akamai. And how many of you know what Akamai is? Okay, some of you know. So for those of you who don't know, Akamai is basically a cloud platform. We have a lot of servers, like really a lot. We have 250,000 servers in more than 130 countries, and we are present within more than 4,000 networks. So with such a big amount of servers, with such a big network, we can do really cool things. Apart from being a CDN, we can also do security and other optimizations. And as for me, I would say that my experience is quite unusual because I started with, let's say, from an academic background, because I worked at the LHCb experiment at CERN, looking for antimatter and writing data quality monitoring system for the experiment. Then, for a bit, I pursued PhD at AGH, University of Science and Technology, and I was working on a project involving applying statistical analysis to aid search and rescue operations by GOPR. After that, I moved to Printbox, where I did some really cool things, and one thing I'm proud of in particular, I implemented an automatic and autoscaler and bidder for AWS EC2 spot market. And as far as I know, this is a service that's been running for 3 or more years without any failure. And yeah, so that's something I'm proud of. And currently, I work at Akamai. I am a frameworks and tools developer. So basically, my job is creating frameworks and tools for other people at Akamai to use and to make their work better. Okay, so this is a photo from Python documentation. I think this is from the first version of Python, which included AsyncIO. By the way, who knows what's the first version of Python with AsyncIO? 3.4. Yes, so those were the times of yield from, which is now maybe not gone, but not recommended to use. But okay, another question: who's ever written any asynchronous code in any language, technology? Okay, most of you. Great. So who wrote that code in AsyncIO? Okay, some of you. So how AsyncIO tackles async code is there's an event loop. It's the core element of AsyncIO, and basically what you do, you put tasks into that loop, and the loop iterates over itself. And when a task is ready, you can get the results, and you can put more tasks into the loop. And it can work because you're putting asynchronous tasks into the loop. So what Python does, it delegates its execution to the OS. So when the OS notifies Python that the task was done, then Python can take the task and fetch data and do something with it. So basically, there's a loop. Then we put some task into that loop. We make some operation, usually it's an IO operation, and then we fetch task when that's ready. So a bit of history to put something to put the entire history into some context. So before Python 3.4, there was a module called async core, which basically had some low-level async operations implemented in it. But not a lot of people used it because it was quite low level. People are used to that Python is high level. So not a lot of people hacked with that. So basically someone submitted a Python idea to a Python ideas mailing list entitled async core included batteries don't fit. So Guido read that email, and 3 months later he created PEP 3156, where he proposed creating AsyncIO. After that, there was a module called Tulip, which first version of it was available for 3.3. And after that, it was officially released with Python 3.4. It was released, but with a small asterisk above it. So the asterisk was that it was released in a provisional version. So basically, they could have introduced any breaking modification without a lot of discussion with the community, and it was like a prototype for people to test. So what was one version earlier, in 3.3, yield from expression was introduced, which allowed yielding from generators. And that expression was used to yield from coroutines, which were introduced in 3.4. After that, there was 3.5, which introduced async await keywords, asynchronous iteration, and asynchronous context managers. And after that, in 3.6, they also added asynchronous generators and asynchronous comprehensions. And actually, starting from version 3.6, they declared that the implementation is stable and that they won't introduce any more breaking changes. So I'm not including here Python 3.7, even though I'm aware that it's been released, because it's not very interesting from the AsyncIO point of view. There are some minor features, of course, and some fixes, but after having basically 3 releases focused on AsyncIO, they shifted their focus a bit for the 3.7 release. Okay, so this is how AsyncIO code looks like. So basically what this code does is it iterates over some collection. The first line is fetching some data from a database, because with AsyncIO and appropriate connector modules, you can run asynchronous queries. So what it does, it fetches asynchronously some data from the database, and then it just runs some tasks after that. So a common misconception about AsyncIO is that everything you do in AsyncIO is asynchronous. And that's not true. You need to specifically call the module in a specific way so it knows that it needs to do its job asynchronously. Because the first thing, the get data coroutine, it is asynchronous, but it has an await keyword in front of it. So basically it means wait until the results are here. So this call is blocking, so you don't get any asynchronous execution here. The second one, on the other hand, it doesn't have an await keyword before it. So what it does, it's exactly what I said 1 or 2 slides earlier. So it just puts this task, this coroutine, into this IO loop, and it just makes sure, it ensures that it'll be executed. So what you can see here, that it's not optimal, because basically on every iteration you have some part of code which is blocking because you have this await. So what you can do with AsyncIO, you can gather a group of coroutines, tasks. So in the second half of the code, what's going on is there is some task which will be run with these parameters. These parameters are, at least the IP parameter is taken from some collection. And then it'll schedule all tasks for all IPs at the same time. And it'll block only when all, it'll block until all these operations are ready. So that's where you gain something from running things asynchronously. Okay, a bit more complicated example, closer to the production code, is that with asynchronous execution, you want to time out at some point if the operation is not done yet. So there's a function for that, wait for. So what you do is you have a, let's say, a big task which it'll take minutes or tens of seconds to perform. So what you usually do in that case is you create a thread pool manager or a process pool manager. You put this blocking task into that manager, which in AsyncIO is called executor. And then you wait for the result from that executor only for a certain amount of time. So basically, you're not blocking with this, at least not from the point of view of that flow. So this is actually our production code, and currently you can do something clever or nicer. You can use asynchronous context managers. So there's a really nice module called async timeout, which basically performs checks whether a coroutine should be timed out or not, and it's much faster than that wait for construction. So if you ever want to time out a coroutine, that's a great tool to do that. Okay, so a lot from what I've said, you could respond to me that, okay, you can achieve that with threads. What you're doing, you're doing some things that you're delegating it out of the main program flow, and then you are gathering some results. So you could do that with threads easily. And actually some languages like Java, I think, they have async implemented, but what you need to do in order to use it, you need to have a thread pool of Java threads to execute your code. So it is similar, but what you gain in AsyncIO is that you're still remaining in the same thread. So with threads, you always need to communicate. You need to give a thread some data. You need to fetch some results back. There are communications and synchronization elements in it. So and also you should not run a huge amount of threads, like hundreds, 500, 1,000, because from the operating system point of view, there will be some additional effects, like rescheduling. The threads will be fighting for the resources, and a lot of communication, as I mentioned. So here you're staying in that single process, in that single thread, and you're delegating work to the operating system. That means that when you execute AsyncIO code, you can only achieve this asynchronous execution when you can actually delegate a work to the operating system. So basically, reading, sending through sockets. There's if you make some calculations, like if you add something, multiply, you cannot delegated outside of the interpreter. Another reason is that actually everyone started doing it in their own way. So async in Python was not introduced with AsyncIO because there were modules that were asynchronous, like Twisted, Tornado, and we live in the age where all services should be asynchronous because we don't want to block, we want to fully utilize our resources. Maybe we are running in a cloud, we want to have a specific control of what's going on. So there were modules that were async, and every module implemented I/O loop, basic interactions with the operating system, and stuff like that. So basically, what core developers wanted is to provide one way to achieve that. And also because async is connected to performance, you don't want to use threads, you want to have good performance, and in order to achieve that, there had to be some modifications to the CPython interpreter implemented to increase that performance. Okay, so now the stories you've been waiting for. So because I'm working with tools and frameworks, we don't have like one specific product that we work on. What we usually do is we create something, we prototype fast, we deploy it, we consult with people who use that. So we have many different tools, we have many projects. So that's why I have a lot of these stories. So the first one is about mixing AsyncIO and threads. So one of the examples before showed you that you can delegate big tasks to some thread pool manager, thread pool executor, and then you can continue your main application flow. And actually, that's quite dangerous because with threads, you get your code is executed out of order. With async, it's executed out of order. So what you get is a bit of a headache when you have a problem and you want to solve it, or even if you want to follow how your system executes in. So yeah, especially if you start developing, if you've never worked on these things before, it's quite complicated and difficult to grasp. So for example, one of the I would say beginner's mistake is that you create a coroutine, you create a future, and it's not being awaited, so you never ever fetch the results of that coroutine. And it might happen even if you're an experienced async programmer, because if you're running a lot of tasks and something unexpected happens and it brings down the entire main thread of the application, this is what you'll see, that some tasks were destroyed or were never retrieved. So yeah, and in case of async tasks, you don't usually get this nice information with error stacks. This is usually what you get. Also, we run into what I would call dependencies nightmare. So this is some extraction of our dependencies. So we had Tornado for HTTP async serving. We had Momoko, which is an async wrapper for psycopg for interacting with Postgres. We had UV loop, which basically is a replacement for AsyncIO in order to improve performance even further. And we had async test to get rid of some boilerplate code. So with this combination, you can see that Tornado is great. We use it all the time. Momoko is pretty dead because there's not much development going on there. With UV loop, you have, because it's a replacement for AsyncIO, and Tornado is already a wrapper for AsyncIO. So what you're doing is you call a wrapper on a wrapper. So that's fun, and it complicates things. And with async test, actually, it's not compatible with UV loop. So for tests, we had to switch it to AsyncIO loop, which is not great because we've learned that some modules, some async modules, rely heavily on the implementation of AsyncIO. So like the async test, for example. So if you switch IO loops, the modules might just start misbehaving. And actually, another fun thing is that we, when we created that service, I think it was in 3.4, and then we had to, when 3.5 arrived, if we wanted to, use the newest, coolest feature, we had to basically change all AsyncIO coroutine decorators, all yield from to async await. And another funny thing is that in Tornado, because it was written before 3.3, they basically yielded. They use just the yield keyword, not the yield from. So in Tornado, when you had Tornado again coroutine, you yielded and not yielded from. So that made some funny confusion at times. But basically, with the transition from 3.4 to 3.5, if you started with that prototype API, you had a lot of work to actually refresh it. Okay. Another story is a story of an asynchronous HTTP client. So we have a project where we want to stream data from many servers, like hundreds, thousands. And it's a basic network operation. We open an HTTP stream and we want to stream data from it. So, nothing complicated. And we used one of the commonly used AsyncIO HTTP libraries to write such an async client which connects to servers, stream data, and only one process, one thread. It was supposed to be great. This is how the core method looked like. So we opened TCP connection, then we created HTTP client, we connected to some server, then we had to call dunder aether because there's no function aether yet. Then if we didn't get any data, we timed out, and if we get some data, then we would use it we would do some processing on it. So nothing really serious. By the way, do you think is that code good, bad, or ugly? Ugly. Why ugly? Yes, so there's too much indentation. So I love context managers, but at some point you need to say enough, because yeah. So what we observed with this application is that it was not the traffic that was increasing. It was the traffic was constant. It was just there was a memory leak in that module. So basically, the memory wasn't recovered correctly. And what we observed is that with the time, Also, the CPU usage went high. So, we contacted the module developer, and till this day, even though we can reproduce it every time, he doesn't know what's going on with his module. So, so that's fun. Okay, another story is about some Elasticsearch client, basically an application that would push some data to the Elasticsearch cluster. And Elasticsearch is great. It's really high performance storage, but it has its quirks. For example, if you put Elasticsearch under constant load, it behaves great. But if there are some increases, if the load increases suddenly or decreases, there's some lags might start to appear. So basically, what we experienced is that if we had any congestion on the network, if we had any lag, and if we, what this application did, it received some input asynchronously, and it was doing some basically string manipulation. It was an ETL application, and then it pushed it to the Elasticsearch cluster. So what we observed is that if we had some congestion and we were not able to push data to Elasticsearch, we had new data that was arriving. And with all that new data, we basically were scheduling new tasks to operate on it and push it to Elasticsearch. And the pusher was also a coroutine, so it created tasks, and we learned that the more tasks you have in your AsyncIO loop, the slower it'll perform. So basically, it's a list, but I guess it takes a lot of gathering notifications from the operating system. So it would basically, at some point, we had so many tasks that we had to just kill the application because it was not able to perform anymore, because the application and the ingestion to the Elasticsearch was slower than the data was coming, and it was solely because there was a lot of data in the buffer. So what we came up, or what we found, is that there's this really great module, AIO jobs, where you can create a scheduler and you can limit, basically you can limit creating to a certain number, creating these tasks, so that your application doesn't blow up either because of using too much memory or becoming really slow. Okay, so I gave you a lot of negative examples, but we've also had, in some applications, we've had really good experience with AsyncIO. So we have this really simple microservice that gets this one job done. So it queries, basically makes DNS queries, and it takes and it makes millions of them. And the first implementation was done using threads, and the data was coming in batches, and it took 12 hours to perform all these queries. And with AsyncIO version, we reduced that to 8 minutes. Oh, okay. And actually, that's sorry, what? Okay. I won't be touching it. And basically, what we've learned recently from the recent projects is that projects that involve queues and message brokers are a really good fit to the AsyncIO applications. Basically, what we use is AMQP, which itself is asynchronous. And if we have services that communicate only through AMQP, that take data and send data through some AMQP broker, we have great architecture, we have simple flow of the application, and it works really great. So, in my opinion, what you gain with AsyncIO is you can gain some performance, especially if your applications are network or DB heavy. You have better resource utilization because you spend less time on communication and synchronization with threads. And what you get in terms of some soft topics, you are on the technological edge. This new tool gives you new ways to solve your problems. And also it forces you to follow Python's progress, because there's so many lacking features that you need to follow Python that you wait for these features. And in terms of cons, so there are still many missing features or known issues that are being year after year they are being fixed. So, for example, async iterators have really messy and indeterministic cleanups, so they are not advised to work in production. Iter tools for async is missing, and also a lot of modules for interacting with popular services either have very early implementations or there's a completely lack of them. And still, AsyncIO is a young implementation with many bugs and incompatibilities. And actually, a problem that's been rising for some time now is that the community becomes more and more divided, because there are already some forks. Like, have you heard about Curio, the thing that David Beasley created? He didn't like AsyncIO implementation, so he created some prototype how it could look if he was the one responsible for it. So, and a lot of modules are actually, even networking modules are not interested in AsyncIO because they either don't believe that it's ready, or they don't like how it's implemented. So, in my opinion, what projects are best suited, and I know that I ran out of time, there's like 2 more minutes. Microservices, like if you have really small service that it's easy, it should be easy to follow the asynchronous execution. Project with a small list of dependencies. So AsyncIO is really incompatible with a lot of the modules. So every release, every upgrade, you need to check whether you don't get any funny results, and you'll never get any guarantees that some problems will always be found during testing and not in production. So simple HTTP APIs, basically if your APIs expose the database through HTTP, it's fine. Projects with big load but light processing, so you get a lot of requests, a lot of traffic, but the processing of each request is really quick. Projects where threads are not enough, so handling 1,000 concurrent connections, for example, that's great in AsyncIO. And projects where you really understand the rest of your stack, so that you know what might happen when you introduce AsyncIO into the picture. In my opinion, projects which are not suited for AsyncIO are projects that heavily rely on threads. So for example, you have something that uses threads heavily, and then you want to add AsyncIO on top of it. Or maybe some of your dependency heavily uses threads. So that's not a good idea too. Projects where you have, when you process either a lot or maybe not a lot, but the processing time of a single task takes a lot of time. And projects doing uncommon stuff. So we often, because everything at Akamai in terms of networking is heavily optimized, all protocols, switches, and stuff like that. From time to time, we had to fiddle with some custom flags or custom SSL connections, and because the modules are really high level, for some of them it's pretty impossible to, for example, get a socket and set some certain flag on it. Okay, thank you very much. I didn't lose my voice. Do we have time for some question? Okay. Let's. In clouds. Actually, what my team does, we have our own cloud based on Marathon and Mesos, and so it's some type of a cloud. So what we experienced is that, at least for the Marathon Mesos thing, the memory and CPU limiting does not always work. So for example, for that application that had a memory leak, we observed that Docker didn't stop at the memory limit that we gave it. So basically, the application could have been running until the server would crash. So that's one thing. In terms of running it on Amazon, for example, no, because there's the problem with running in the multi-tenant environment is that you might be put on a host that is running that it's a multi-core host, and that is running, like a lot of I/O stuff or a lot of CPU-bound stuff. So if your AsyncIO application lands on that host, you might experience big delays, because basically the CPU will be waiting to have its I/O lines ready for your application. There will be a lot of context switching. So I wouldn't say it's dangerous in any way, but you need to be ready that it will it might perform worse than running on your own environment, and you need to be ready, like always in the cloud, that you might experience connection issues, network issues, all kinds of failures. Mm-hmm. Mm-hmm. Yeah, so currently AsyncIO is a really huge buzzword in the Python community. So basically all mainstream Python blogs are covering it or have covered it already. So I would say that going through the documentation of the AsyncIO module and later trying to write some really simple stuff like async HTTP server or async HTTP client. That's a good point to start. I wouldn't recommend starting with asynchronous queries to the database, because the connectors are not perfect and they are usually wrappers for other connectors. So it makes the entire thing more complicated. But there's 2 or 3 years ago there was little to none information, modules, examples on how to write AsyncIO code, and now I would say the internet is full of it. So it should be easy to find something interesting. Yes. Mm-hmm. Yeah, so because Curio, I think, is not something that's production ready, and it's not something that's supposed to be production ready. So what David Beasley wanted is to show that you can implement it in a simpler way, in a better performing way, and it was supposed to be like a conversation starter with Python core developers to maybe use some of the code and introduce it to AsyncIO. But as far as I know, the module was just to present that, and it's not being maintained and developed in a way such as it can never replace AsyncIO, especially on production systems. But I think it's the implementation is much simpler, and because of that, it performs much better. But we don't have any applications running Curio.
Okay, thank you very much.
Okay, thank you.